What if the first message we receive from an alien intelligence isn't a greeting, but a warning? A warning not about them, but about the very nature of reality itself. Imagine a transmission, decoded after centuries of listening, that simply says, "Don't look past the edge. Something is listening." But the edge of what? Not our solar system, not our galaxy, but the absolute boundary of our universe. What could possibly exist out there that would terrify a civilization far more advanced than our own? In this documentary, we'll venture to that very edge, to the threshold of established science, and into the great unknown. We'll investigate every chilling possibility that awaits. From infinite copies of our own reality to the shattering collision of cosmic bubbles, and the silent, all-encompassing void of absolute nothingness. The observable versus the entire universe. The portion of the cosmos that we're able to perceive with our instruments measures roughly 93 billion light-years from one side to the other. This immense size is a direct consequence of the universe's expansion since the Big Bang. Over the 13.8 billion years of cosmic history, the very fabric of space between galaxies has stretched profoundly. Light from the most remote corners of existence has only now completed its epic journey to reach us, which in turn establishes a boundary we simply cannot see beyond. This isn't a technical hurdle we can solve with superior telescopes or deeper knowledge. It's a fundamental restriction woven into reality. Since the beginning of time, no matter how powerful your observatory, you can't peer past the veil imposed by the finite speed of light. And this is where it gets truly mind-bending. Beyond that cosmic horizon, the universe could stretch on forever. Picture yourself adrift in a vast, dark ocean at night. Far in the distance, you see a shimmering circle of city lights. This is the only sign of civilization you can witness. You have no way of knowing how far those urban centers extend, or if that's even where the land ends. That glowing ring is a perfect analog for the universe we can observe. It's just a tiny sliver of the whole, a limitation created by the colossal journey light must undertake to find us. Beyond it could lie more stars, more galaxies, more of the science we know, and maybe even phenomena we haven't yet begun to imagine. So, how can we possibly describe the entire universe? This is a question that dances on the line between scientific inquiry and philosophical contemplation. The observable universe is the canvas for our studies, but the full universe includes everything that is, and the gap between these two could be staggering. Many scientists embrace the inflationary theory, an addition to the Big Bang model, suggesting that the universe expanded at an unbelievable rate in the first moments after its birth. It was during this hyper-expansion that tiny quantum fluctuations were magnified across enormous distances, setting the stage for the large-scale structures we see today. But inflation doesn't have to stop everywhere at the same time. In many models, it carries on indefinitely. This idea is known as eternal inflation, and it opens the door to the speculation that our universe is merely one pocket world among a countless, perhaps infinite number of others. If inflation did indeed rage on beyond our cosmic viewpoint, then there could be a nearly endless expanse of universe out there, in some places looking just like our own, and in others fantastically different. Galaxies might coalesce under the same rules of gravity and thermodynamics, or perhaps other domains have different settings for the fundamental constants of nature, making life, matter, or even atoms as we know them, impossible. We would be forever oblivious, as no signal or information can travel to us from those distant realms. The fact that we're isolated from the vast majority of the universe is a built-in feature of physics. The speed of light isn't a mere guideline, it's the ultimate velocity, and there is no known method to cheat it. In essence, the cosmos might be unending, but our understanding will forever be limited to the small patch we can actually see. Some cosmologists are trying to estimate the size of the entire universe by examining the shape and curvature of space. So far, every measurement we've taken suggests that space is geometrically flat. If this is true on the largest scales, it could mean the universe extends infinitely. Yet, it's also plausible for the universe to be finite in size even with flat geometry. It could be that it cleverly wraps around on itself in complex and fascinating ways. In a universe like that, you could theoretically fly in a straight line for billions of years and never find an edge. You would just arrive back where you started. That said, when we look at the cosmic microwave background, the most ancient light in the universe, which comes from just 380,000 years after the Big Bang, we find patterns that suggest a uniformity that extends far beyond our observable boundary. There is no obvious border, no sign of a cosmic wall, and no sudden end to the stars, just more of the same as far as our instruments and light itself can show us. However, the difference between the observable and the entire universe is more than just a detail. It fundamentally changes our place in the cosmos. If the universe is infinite, then the region we can witness is just a tiny speck in an endless sea of the unknown. It's possible that one day we might be able to map its full shape, or maybe we'll pick up strange signals that have traveled across the curvature of space to reach us. Regardless, the sky we see is not the end. It's simply the farthest that light has managed to reveal to us, and even that is constantly, slowly changing. Every second, light from ever more distant regions finally arrives. The observable universe is getting bigger, but in a cosmic irony, the galaxies beyond our reach are also speeding away faster and faster due to dark energy. Some galaxies we can see today will one day become permanently unreachable, their light stretched into nothingness. The edge, in a sense, is both approaching and receding at the same time, a cosmic tide we can never catch. When someone talks about the edge of the universe, know that it's not a wall, a cliff, or a final destination. It's a boundary drawn in time, not space, a limit dictated by the speed of light and the ceaseless expansion of the cosmos. And beyond that, perhaps more galaxies, perhaps another universe, or perhaps the end of physics as we know it. The horizon of time. When we talk about the edge of the universe, we tend to picture a remote frontier or a dividing line with something on the other side. More space, a physical barrier, or just emptiness. Modern cosmology, however, turns this idea on its head. The real boundary of our universe isn't in space, it's in time. To get a feel for this, think of the universe as an inflating balloon. You're a tiny point on the balloon's surface, and as it blows up, all the other points move away from you. Now here's the key insight. The surface of that balloon has no edges. The only edge is the limit of your vision across its surface, and that boundary isn't set by distance, but by time. This limit is what we call the cosmic horizon, and it's defined by the age of the universe. Light takes time to travel, so when we look deep into the cosmos, we're also looking back into the past. The most distant light we can currently detect comes from about 13.8 billion years ago, right around the time of the Big Bang. But because space itself has expanded since then, that light is now coming from regions that are about 46 billion light-years away from us. This gap between travel time and current distance is a core feature of cosmic expansion. So, when we ask what's beyond the observable universe, what we're really asking is what exists beyond the reach of light that's had enough time to get here since the universe began. The edge, therefore, isn't a spatial boundary but a temporal one. Imagine lighting a candle in a huge dark cave. At first, the light only shows you your immediate surroundings. As time goes on, the glow spreads, lighting up a larger and larger circle. The edges of that light aren't the edges of the cave. They just show how far the light has managed to travel in a certain amount of time. In the same way, our telescopes can only see as far as photons have had time to journey through the expanding fabric of the universe. This concept is called the particle horizon, and it marks the greatest distance from which particles could have traveled to an observer over the age of the universe. But there's another horizon that might be even more mind-boggling, the event horizon. While the particle horizon tells us the limit of what we can see right now, the event horizon tells us the limit of what we can ever see, even if we wait for an infinite amount of time. This is because dark energy is making the expansion of the universe speed up. We can see certain galaxies today, but they're moving away from us faster than the speed of light because of the expansion of space itself. It's not that these galaxies are zipping through space, it's that space itself is stretching between us and them. Because of this, their light will never reach us again. One day, they'll be permanently beyond our view. This means there's a cosmic cutoff, not just in what we can see now, but in what we'll ever be able to see. The universe, in a very real way, is slipping away from us. This horizon of time, though, does more than just limit our vision. It sets the boundary for our knowledge, our scientific models, and even our ability to find meaning. Beyond this temporal veil, there could be entire civilizations, galaxies, or even systems of physics that we'll never know about, not because our technology is too primitive, but because the very structure of reality forbids it. And yet the horizon of time isn't fixed, it's dynamic. With every passing second, more photons arrive, giving us a deeper look into the past. New discoveries are made possible with every moment. When the James Webb Space Telescope peered farther into the cosmos than any instrument before it, it was stretching our temporal horizon, catching light from just a few 100 million years after the Big Bang. In doing so, it deepened our understanding not just of the universe's scale, but also of our own place within cosmic time. There's a philosophical side to this as well. The time horizon serves as a psychological boundary, not just in a cosmic sense, but in how we think about existence itself. The idea that some parts of the universe will forever be out of reach, unseen and unknown, forces us to wonder what it even means to exist. If there are galaxies whose light will never find us, do they truly exist in our universe, or are they effectively separate realities? Then there's the problem of simultaneity, or the difficulty of defining now, for observers who are incredibly far apart. In relativity, time and space aren't absolute. There are cases where two events that happen at the same time for one observer don't happen at the same time for another. On a cosmic scale, this is more than just a thought experiment. It limits our ability to talk about the present moment in a universe where motion and gravity make clocks tick at different rates. When we see a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago. But what is it doing now? That question has no meaning in relativistic terms unless we define a specific frame of reference, which isn't easy in cosmology. Our now is local. Every region of space has its own version of the present. So even if we could break through the horizon of time, we'd be stepping into another entity's past or future, not a shared present. Time, in this sense, is the ultimate boundary, not space. This realization fundamentally alters how we picture the universe's edge. There's no wall, no fence, no limit we could travel to and eventually touch. Instead, There's a vast and ever-growing silence, a boundary defined not by distance, but by delay. And for some phenomena, that delay is infinite. Their light will just never get here. But this is also a beautiful thing, because time is what lets us perceive the universe at all. If there were no temporal limit, no distance, everything would collapse into a single, static instant. It would be flat and lifeless. Instead, the universe unfolds slowly, like a story told through light, with each photon carrying a piece of the narrative across the ages. Is the universe finite or infinite? Is the cosmos limited, or does it go on without end? This stands as one of the deepest and most unresolved questions in science. To tackle it, we first have to separate what we can observe from what might actually be out there. The observable universe is a sphere of space roughly 93 billion light-years across. This doesn't in any way mean the universe is 93 billion years old. The reason for this discrepancy is that while the universe is only about 13.8 billion years old, space has been expanding for its entire history. The light from the most distant galaxies has been traveling for 13.8 billion years, but because of this expansion, those galaxies are now located about 46 billion light-years away from us. That sets the size of our observable bubble. But what's beyond it? There are three main possibilities, each more mind-bending than the one before. 1. The universe is finite but unbounded. This idea is tricky to get your head around. Think about the surface of the Earth. If you walk in any one direction, you'll never fall off an edge. It's true that the Earth has a finite surface area, but it's also true that it has no borders or edges. With enough supplies, you could walk forever and never hit a wall. Now, take that two-dimensional analogy and imagine it in 3 dimensions. In this model, the universe could be like a 3-dimensional version of a sphere's surface. It's finite, but it curves back on itself. If you could travel in a straight line for a long enough time, faster than the universe is expanding, you might eventually come back to your starting point. Just like someone walking around the Earth ends up back where they started. This kind of universe would have what's called positive curvature, similar to the geometry of a sphere. But here's the catch. There's no visual curve that your eyes could see, because it's space itself that's curved, and you're moving within it. Every step you take feels straight. It's the universe that's looping, not your path. 2. The universe is truly infinite. Many cosmologists lean toward this view. In this model, space extends forever in all directions. There is no limit, no edge, and no path that brings you back to the beginning. There's just an infinite universe stretching out endlessly, filled with galaxies, dark matter, radiation, and maybe even physics we can't yet dream of. If the universe is infinite, it comes with some incredible consequences. One of them is that there might be another version of you out there. In fact, there could be an infinite number of you. Why? Because there's a finite amount of matter in the universe and only a finite number of ways to arrange it. Therefore, every possible arrangement has to repeat itself eventually. It's like rolling a die enough times. You're guaranteed to get the same number again. This idea is known as the cosmic doppelganger hypothesis. This isn't science fiction, it's a logical consequence of an infinite number of chances. Our observable universe is just a drop in an endless ocean of galaxies, a small patch of sky in a cosmic field that has no end and can never be fully known. How, then, can we test for infinity? The truth is, we can't, at least not directly. We're unable to send probes beyond the horizon. We can only observe what's inside our visible sphere. That's why we have to rely on mathematics. 3. The universe is flat, and that might mean it's infinite. We can get a sense of the universe's overall size by studying its shape. Using geometry, we've figured out that the universe is almost perfectly flat. This conclusion comes from studies of the cosmic microwave background, CMB, particularly from the WM8 and Planck space probes. Flat geometry is what you'd expect to find in an infinite space. If you draw a triangle on a flat sheet of paper, its angles add up to 180 degrees. That's flat geometry. If you do the same on a sphere, the angles sum to more than 180 degrees. That's positive curvature. If you do it on a saddle-shaped surface, they add up to less. That's negative curvature. The fact that our universe appears flat suggests either that it's infinite or that it's so incredibly vast that any curvature is too subtle for us to detect, much like trying to prove the Earth is round with your naked eyes while standing on a beach. This is also tied to the concept of cosmic inflation. The universe expanded extremely rapidly in the first fraction of a second after the Big Bang. In the same way that inflating a balloon makes a small patch on its surface seem flatter, this rapid expansion smoothed out any initial curvature. If inflation went on long enough, which we think it did, the observable universe would look flat. This is true even if the universe as a whole is curved on much larger scales. Where things get really strange is with the idea of a finite yet edge-free universe. Even if the cosmos is limited, there's no such thing as an outside. You can't point to a wall or an edge. A finite universe doesn't need a cosmic fence, just like the surface of a balloon doesn't need an edge. It's as if a hypersphere were curving through higher dimensions. Space could be closing in on itself. You would never reach an end because there isn't one. The journey would just keep cycling you back through space-time. This brings us to a major philosophical shift. The universe isn't expanding into anything. It's expanding within itself. Space is being created between objects, not at some outer rim. In fact, asking what's outside the universe might be a meaningless question, like asking what's north of the North Pole. In general relativity, space and time are the fabric of the universe. Without them, there's no framework in which outside can even exist. The implications of a finite versus an infinite universe are profound. Whether the cosmos is limited or endless changes how we think about everything, from the ultimate fate of the universe to how we define meaning and whether we're truly alone. If there are limits to the universe, then we might be part of a closed loop or a cosmic island, with boundaries written into the laws of physics. For instance, there might be only one Earth and one you. If it's endless, however, the story gets much weirder. There could be multiple versions of history out there. Every possible outcome, every wish or fear could be playing out in some distant corner of the multiverse. Space expands. But into what? If there's one question that consistently stumps the minds of even professional physicists, it's this. If the universe is expanding, what's it expanding into? At first, it seems like a simple question. A balloon expands into the air around it. A drop of ink spreading in water expands into more water. Everything we see in our daily lives expands into something else. It's only logical to assume the universe is expanding into a bigger empty space, like a vast cosmic chamber. But the reality is far more bizarre. The universe isn't expanding into anything. According to general relativity and our best models of the cosmos, it isn't pushing into some pre-existing void. Instead, space itself is stretching. Objects are getting farther apart, not because they're traveling outward into a larger container, but because the container itself is growing. Let's break that down. In cosmology, to understand expansion, we need to think about the concept of the metric, which is the mathematical tool that describes distances in space-time. In an expanding universe, the metric isn't fixed. A part of the metric, known as the scale factor, increases with time. What does this mean in simple terms? It means that over time, the very ruler we use to measure space is itself growing. Two galaxies that were once 1 billion light-years apart might now be 2 billion light-years apart, not because they've moved through space, but because the space between them has literally expanded. This idea is baked into the Friedmann-Lemaitre-Robertson-Walker FLRW metric, a solution to Einstein's field equations that describes a homogeneous, isotropic, expanding, or contracting universe. It shows how distances between objects change over time because of the dynamic geometry of space itself. From this viewpoint, space isn't growing inside a box, it's just getting bigger. There's no sharp edge or boundary, and therefore no outside. A popular analogy used to explain this is the inflating balloon. It's like putting small dots on the surface of a balloon. The dots move away from each other as the balloon inflates. They aren't moving across the surface itself is stretching. Now, imagine that surface as a two-dimensional universe. It grows larger, but there's no center on that surface. Every point sees all the other points moving away from it. However, this comparison also leads to confusion. We inflate a balloon in a room, the balloon is expanding into the air around it, which is a third dimension beyond the surface. Because of this, when we think of the universe expanding, our minds instinctively try to imagine a fourth dimension that it's growing into. But here's the crucial point. Our models don't require any external dimensions. There is no outside to the universe. It's a self-contained, dynamic entity. The expansion doesn't need an external medium. Space is simply getting bigger. Another common misunderstanding is that the universe is expanding outward from a central point. That's not how the expansion of space works. In our universe, every point sees every other point receding from it. There is no center. From a galaxy 10 billion light-years away, you would see the same thing we do, galaxies rushing away in every direction. The universe appears to expand around every observer. In a universe that is homogeneous, the same everywhere on large scales, and isotropic, the same in all directions, there's no center at all. This doesn't mean each of us is the center of the universe. The expansion isn't linear, it's geometric. What's past the edge, then? There's nothing there, not even space, as we understand it. It's not that there's a void out there waiting to be filled. There's no place outside of the universe. The concept of beyond doesn't apply here, at least not according to our current scientific models. There's no space, time, or structure outside of the expanding cosmos. According to some theoretical models like brain cosmology, the universe could be embedded in higher dimensions, with our universe being a brain floating in a higher dimensional bulk. In that scenario, it's possible the universe is expanding into a space with more dimensions, but that's not what standard general relativity describes. For expansion to happen, you don't need to assume an embedding space. Expansion can be explained entirely by the internal dynamics of the universe. You can measure the distances between galaxies, how fast they're moving away, and how their light is redshifted without ever needing to talk about an outside. Another way to think about it is this. When we use the word expansion, we usually mean that something is growing into something else. In the case of the universe, however, expansion means that more space is being created, more distance, not into something else, just more. We're not completely unfamiliar with this idea. Every second seems to appear out of nowhere, but we don't ask what time is expanding into. Time just passes. On a cosmic scale, the same is true for space. Looking back in time, this makes sense too. As we go further back in time, toward the Big Bang, the universe gets smaller, denser, and hotter. If you trace this process back, the scale factor will eventually hit zero, a point we call a singularity. We don't believe it shrank from something larger, though. It was what it was, small and self-contained. Moving forward, the same principle applies. It just gets bigger. It's not growing into anything. At this very moment, there is simply more space being created. People have wondered for millennia what lies beyond the stars, at the edge of the sky, and at the end of the universe. That boundary has been pushed further with each scientific revolution, but as the universe expands, we're faced with something we've never encountered before. There is no edge at all, and this can be unsettling. We want edges for safety. We need a box to contain things. Our brains have evolved to think of objects in rooms, seas on planets, and galaxies in universes. The universe, however, isn't an object. It's a field, a shape-shifting, law-governed framework of space-time. The question, what lies outside the universe, might be like the question, what lies outside mathematics? It's a question that could be meaningless, with no possible answer. Still, we ask because we're explorers, not just of seas, stars, and atoms, but also of ideas too vast to be contained in words. What the universe is expanding into isn't just a question of cosmology, it's also a question about the limits of our own imagination. The universe has no center. When you're floating in the immense void of space, surrounded by so many galaxies that the darkness itself seems alive, you might wonder where the center of it all is. Where did the Big Bang actually happen? From what single point is everything expanding? The truth, however, is that the universe has no center. It didn't explode in space like a bomb from a single location. It wasn't a blast that erupted outward into a pre-existing void. The Big Bang didn't happen in a specific place, it happened everywhere at once, because that's the moment when space itself was created. Imagine an infinite sheet of rubber being stretched in every direction simultaneously. There are points on that sheet that move away from each other as it expands. No matter where you stand on that sheet, everything appears to be expanding away from you. But there's no special spot. There is no center. There's just more rubber being created everywhere. That's a good way to think about how our universe works. When we look out into space, we see galaxies moving away from us in all directions. The farther away they are, the faster they seem to be receding. This is known as Hubble's law, and it's true no matter where you are in the cosmos. From a galaxy 10 billion light-years away, you'd observe the exact same thing, galaxies rushing away from you in every direction. It would give you the illusion that you're at the center, but that illusion is universal, because the universe isn't expanding from a place. It's expanding between places. This is one of the most profound and difficult ideas in cosmology because it goes against our everyday intuition. We're used to objects having centers. Our planet has a core, our galaxy has a central supermassive black hole, and even a hurricane spirals around a central eye. But the universe, it has no edge, no outside, and no middle. The universe is homogeneous, meaning it's the same in all locations on large scales, and isotropic, meaning it looks the same in every direction. These two principles, together known as the cosmological principle, are foundational to our best models of the cosmos. And yet, it just feels wrong. How can everything be expanding if there is no single point of origin? How can there be motion without a center? Let's use the balloon analogy again, but carefully. If you inflate a balloon and draw small dots on its surface, those dots will move away from each other as it expands. None of them are at the center of the expansion. While the true center of the inflation is inside the balloon, the surface of the balloon is our analogy for three-dimensional space, which is represented by 2 dimensions in this comparison. This means the center isn't on the surface. It doesn't exist in the world of the analogy. In the same way, the center of our universe isn't located anywhere in space. It's not in any specific place. Or maybe it's everywhere. When we say the Big Bang happened everywhere, we mean that it wasn't an explosion that threw matter into a pre-existing space. Instead, space itself was once smaller, hotter, and denser, and then it expanded. As it grew, so did the locations we used to describe it. There was no outside for it to expand into, and no fixed point for it to move away from. In this way, the universe is like a seamless fabric with no threads leading to a middle. And if that's not strange enough, consider this. Even if the universe is finite, like the surface of a sphere, it can still have no center. Think about being on Earth. You can walk in a straight line forever without falling off or hitting a wall. Earth is a finite sphere, but it has no edge, and no point on its surface is the center of that surface. It's simply curved in a way that loops back on itself. If our three-dimensional world has a similar shape, like a hypersphere, then it might be limited in size, but not in scope. There are no walls, no edges, and no middle. That's why the answer to where did the Big Bang happen is right here, and also everywhere else. All of space and time were once compressed into that unbelievably hot and dense state. This isn't just an abstract idea, it's supported by observation. We can see that the cosmic microwave background radiation is coming at us from all directions with almost perfect uniformity. You wouldn't expect that if there were a center somewhere. The fact that it's everywhere is like the lingering echo of a universal beginning. We're not off to the side in some distant neighborhood of space far from the main event. We're also not the most important thing in the universe, nor are we at its center. We're just a small part of a vast, expanding whole. Nowhere is the center, and everywhere is somewhere else. And that truth might be the most humbling of all. The holographic principle. Visualize yourself holding a snow globe. Inside, there's a tiny world, maybe a winter village or a castle surrounded by a magical flurry. Now, imagine being told that everything happening inside that globe, the physics of the scene, down to the last snowflake, the gust of wind, and the flow of time, is somehow written on the surface of the glass. Not just a picture, but the entire physical reality, encoded in 2 dimensions on the outside. That's the core mind-bending idea behind the holographic principle. It suggests that all the information about our 3-dimensional universe, including every single thing that happens within it, might actually be described by information stored on a distant 2-dimensional boundary, a kind of cosmic screen. Like a hologram, the 3D world we see and touch might be a projection of a deeper, lower-dimensional reality. To understand why physicists would even entertain such a wild notion, we have to start with black holes. In the 1970s, physicists like Jacob Bekenstein and Stephen Hawking began to investigate the thermodynamics of black holes. They stumbled upon something astounding. The amount of information or entropy that can be held within a black hole is proportional to the surface area of its event horizon, not its volume. This was bizarre. In most physical systems, entropy, which is a measure of disorder or the number of possible microscopic arrangements, scales with volume. A room full of gas molecules, for instance, has an entropy that depends on the space the gas fills. But black holes behave differently. The amount of stuff a black hole can contain seems to depend on its skin rather than its guts. One bit of information is smeared across a Planck area, which is the smallest conceivable area of space, equal to about 1035 meters squared. This led to a strange but powerful idea. Maybe black holes are just a clue. maybe this is how the entire universe works. This brings us to the holographic principle, first put forward in the 1990s by Gerard T. Hooft, and later developed by Leonard Susskind. It proposes that all the information contained within any volume of space, even our whole observable universe, could be encoded on its boundary surface. It's a radical break from how we normally think about reality. But in 1997, it gained serious credibility through a breakthrough known as the ADS-CFT correspondence, a mathematical duality discovered by theoretical physicist Juan Maldacena. In short, there's a mathematically identical description that lives entirely on the boundary of a specific type of spacetime called anti-de Sitter space, ADS. This boundary description is a conformal field theory, CFT. Equations on the outside can perfectly describe everything happening on the inside. This holographic duality is a powerful tool in string theory and quantum gravity. A world with gravity and a world without gravity can be two sides of the same coin, even though they seem completely different. Our universe isn't ADS space. It's a flat or slightly positively curved space-time. However, the connection points to a deeper possibility. Maybe our universe is also a projection. If this is true, it would change everything about how we see ourselves. Just think about it. What if the very edge of the universe contains the information for every planet, star, particle, and moment in time? It could even be on the cosmic horizon, which is the farthest distance light has had time to travel to us since the Big Bang. That edge, which is 46 billion light-years away in all directions, could be acting as a screen, a flat surface that stores the quantum information of everything inside it. And we, living our three-dimensional lives, are simply experiencing the projection of that information as physical reality. But how could this be? How could we be shadows of something more fundamental? Let's go back to holograms to help wrap our minds around it. You can find them on credit cards or novelty items. When lit up correctly, a flat surface with microscopic interference patterns can create the illusion of three-dimensional depth. There's a huge amount of information on the surface, but the experience feels like it has volume. When you apply the holographic principle, this analogy is taken to its ultimate conclusion. It's not just an illusion of depth. Everything in reality, from quarks to consciousness, might originate from a deeper 2D layer that we can't directly perceive. Of course, this is still highly theoretical. We don't yet know if the universe truly works like a hologram, but there are some tantalizing clues. For instance, the entropy limits derived from holographic arguments match those found in cosmological models. Efforts to unify quantum mechanics with general relativity, especially in quantum gravity research, find common ground in holographic methods, and in some models of the early universe, the inflationary period might have imprinted holographic information onto the cosmic microwave background, subtle signals that astronomers could one day hunt for. It also has profound philosophical consequences. What does it mean to be in a certain place if the universe is a hologram? Does space itself emerge, meaning it's not a fundamental thing but a useful illusion? Is gravity really just the manifestation of more complex quantum interactions happening on a flat surface somewhere beyond our perception? And here's a truly strange thought. If reality is stored on a surface, what's on the other side of that surface? What does the holographic principle mean for our search for the edge of the universe? There might not be a wall in space. If there's a boundary, it might be a boundary of information, a place where the data describing our universe is stored, like the edge of a hard drive where a program is written. This edge might not be in space at all. It could be mathematical, existing in code, in the logic of pure quantum information. So the holographic principle doesn't just point to what might be outside of space and time, it redefines the entire question. The edge might be the code itself. The execution of that code is what we see, hear, feel, understand, and even think. We still don't know for sure, but by even thinking about it, we're already pushing the boundaries of what's real. Brain cosmology. What if the universe we live in is just a tiny part of a much larger, more intricate reality? This is the core concept of brain cosmology, a theory that grows out of string theory and suggests our universe is a three-dimensional fabric, or brain, floating within a higher dimensional space. The term brain comes from the word membrane, but you won't find it in a biology textbook. It's a theoretical idea that could completely change the way we think about existence. In our daily lives, we experience three spatial dimensions: up, down, left, right, forward, backward, and one dimension of time. But string theory, the mathematical framework that tries to unite all the forces of nature, suggests that more dimensions might exist. In some versions, there are 10 or even 11 dimensions. Most of them are compactified, meaning they're curled up so tightly on scales too small for us to notice, but a few might be extended in ways that allow entire universes like ours to exist as 3D brains floating inside a higher dimensional space called the bulk. In this picture, we're stuck on our brain. Everything we know, atoms, light, gravity, mostly, planets, and even ourselves, is confined to this 3D surface. The particles and forces of the standard model of physics are localized to the brain, which means they can't wander off into the higher dimensions. But the bulk, the multidimensional space where brains live, could be home to other brains, other universes, and maybe even entirely different laws of physics. This leads to some incredible consequences. One of the most fascinating aspects of brain theory is that it suggests there could be other brains moving around in the higher dimensional bulk. These brains could be other worlds, each with its own galaxies, matter, time, and perhaps even different forms of life governed by different physical laws. Gravity is one of the few forces that might be able to leak into the bulk, so even though we can't directly interact with these other brains, we might still be able to feel their gravitational influence. This idea helps solve a long-standing puzzle. Why is gravity so much weaker than the other fundamental forces? If gravity can spread into extra dimensions while other forces are stuck on our brain, then the gravity we feel is diluted, weaker than it is elsewhere. This leakiness could be a clue that higher dimensional realities aren't just possible, but necessary. One theory, called the ekpyrotic universe, suggests that the Big Bang wasn't the beginning of space and time, but rather the result of two brains colliding with each other. When they crashed in the higher dimensional bulk, they released a huge amount of energy, enough to kickstart the rapid expansion of our universe. From one perspective, this brain collision would look like what we call the Big Bang. From another, it was a cosmic rebound, part of an endless cycle of collisions and expansions. Imagine two giant invisible sheets moving through an ocean of other dimensions. When they collide, boom, a universe is born. Then they move apart, and the process begins all over again. From this point of view, the universe isn't a one-time event, but a cyclical process with no real beginning or end. What else exists besides our world in this model? There could be a whole family of universes or other brains with their own laws evolving in their own ways. Some might be completely alien, filled with strange matter and geometries that are impossible to imagine. Others might look almost exactly like ours. There are also some that could be just microns away from us, less than the width of a human hair, but are forever unreachable by normal means. There's also the fascinating idea that brains could still collide. If another brain crashed into ours again, It might trigger a new Big Bang in our space, which could reset or even destroy our universe. These aren't just ideas from science fiction. They are theoretically possible consequences of string theory. It's hard to test brain cosmology because we can't directly see extra dimensions or other brains. Yet scientists are searching for indirect clues. For example, it's possible for gravitational waves to carry echoes of their interactions with other brains. Tiny variations in the cosmic microwave background could be signs of brain collisions that happened in the distant past. Particle accelerator experiments, like those at CERN, might find evidence of extra dimensions or particles escaping into the bulk. What does this mean for the universe's edge? The concept of an edge is transformed in brain cosmology. There's no wall or black hole at the end of our world. Instead, it's like a sheet floating in a deeper reality, with no edges within our own dimensions. If you kept traveling in the same direction, you'd always stay on the brain. If it loops back on itself, you might circumnavigate it, but you'd never leave it. You'd have to move into a completely different plane to go beyond, which might not be possible for beings like us. Unless, and this is a very big if, there are quantum tunnels or wrinkles in spacetime where the brains touch. For now, these are just speculations, but the idea is a rich playground for both science fiction and theoretical physics. In what part of the universe does the fabric of our existence thin out? Could we see or even touch another world? Bubble universes. What if our universe is just one bubble in an immense cosmic ocean? What if there are countless others constantly popping into being? This is the stunning concept behind bubble universes, an idea that emerges from the theory of eternal inflation. It completely changes how we think about what might exist beyond the edges of our observable universe. It would mean that our cosmos isn't unique, and that the vast reality we know is just a tiny piece of a multiverse far grander than we can possibly imagine. First, let's talk about cosmic inflation, which was an incredibly short but explosive event that happened a tiny fraction of a second after the Big Bang. The theory of inflation suggests that space didn't just expand, it expanded faster than the speed of light. This smoothed out any initial irregularities in space-time and explains why the universe looks so uniform today. Many scientists accept this idea, and observations of the cosmic microwave background strongly back it up. However, some theories about inflation, especially those that come from quantum field theory, suggest that it never really stopped everywhere. Instead, eternal inflation proposes that while inflation ended in some regions, it continues in others. These quieter areas, where inflation stops, give rise to bubble universes, separate pockets of space where the rapid expansion slows down, allowing galaxies, matter, and life to form. It's like a bubble formed around us, but there could be a huge number of others. The laws of physics could be different in each bubble universe. There could be different particles, forces, and even dimensions. In some, gravity might be stronger, stars might not form, or atoms might not be able to hold together. In other places, conditions might be even more favorable for life than they are here. And what's even stranger is that they might be forever out of reach, expanding away from each other faster than light, and their boundaries disappearing as quickly as they form. So, how do these bubbles form? The mechanism comes from the quantum fluctuations of a hypothetical field called the inflaton field, which is what drives inflation. Think of the inflaton field as a sea of energy. Every now and then a fluctuation happens that's strong enough to push a region of space into a lower energy state. This transition makes inflation stop locally, forming a bubble. Meanwhile, the rest of the field keeps inflating, creating more and more bubbles over time. The process is self-replicating, like a cosmic popcorn machine that's eternally popping. This gives rise to the multiverse, not in the science fiction sense of parallel timelines, but in the physical sense of a landscape of bubble universes, each with its own version of reality. But will we ever be able to see these other worlds? This is where it gets tricky. Space is expanding faster and faster, so other bubbles are typically very far away from us, separated by vast regions of space that are still inflating. They're moving away from us faster than light can travel because of inflation, so we can't see them directly. However, some scientists think that if two bubbles were to collide, it might leave a faint circular mark on the cosmic microwave background, like a stone hitting water and creating a splash. As of now, no such definitive trace has been found. Some strange anomalies, like the mysterious cold spot in the CMB, have led to speculation that they might be the imprints of bubble collisions from the distant past. Bubble universes have philosophical and even spiritual implications that go beyond science. In a multiverse that's eternally happening, every possibility is realized somewhere. In a different world, Earth might have taken a different path, and dinosaurs might not have gone extinct. In another, the laws of nature are just a fraction different, enough to prevent any life from forming. And in yet another, advanced civilizations rose and fell long before ours. There may even be copies of you living in universes that are similar to yours but slightly different, created by the roll of different quantum dice. Some physicists support this idea, arguing that the multiverse is why our universe seems so perfectly fine-tuned for life, stars, and planets. It's not that the universe was made just for us. We just happen to live in a bubble where the conditions are right, because no one could survive in the billions of other places where they aren't. But some people disagree. They argue that the multiverse might be unfalsifiable because it can't be directly tested, which means it's outside the realm of normal science. Can the idea ever be proven if we can never observe another bubble? Evidence is still being gathered indirectly. Eternal inflation comes from known science. It doesn't require any strange new theories. And if other predictions of inflation match our observations, like the structure of the CMB, it adds more weight to the overall framework. It's even been suggested that the flatness and uniformity of our universe are best explained by the idea that it's just one bubble among many. What does this mean for the edge of the universe? In the bubble universe model, the edge isn't a place in space, but the boundary of inflation itself. Our universe was born from a bubble where inflation stopped, surrounded by a storm of space that's perpetually expanding. Trying to reach that edge would be like swimming upstream in a river that flows faster as you go. You can never get there, and the water never stops moving. But in theory, if a method were found to punch through the inflating barrier, a kind of quantum tunneling into another bubble, we might find ourselves in a universe with completely foreign laws. Most likely such a journey would be instantly fatal, as the energies involved would tear apart any familiar matter. But the idea remains one of the boldest frontiers in cosmology. The ekpyrotic universe. Imagine the universe as a whole, with all its galaxies, stars, and planets, not starting in a fiery explosion from a single point, but through a cosmic clash, a deliberate, slow, but incredibly powerful collision between two immense cosmic sheets. This is the idea behind the ekpyrotic universe, a very different origin story from the standard Big Bang model. The term ekpyrotic comes from the ancient Greek word ekpyrosis, meaning conflagration or out of fire. It refers to a recurring cosmic event described by the Stoic philosophers, where the universe cyclically burns and is reborn. In modern cosmology, the term has been adopted to describe a theory rooted in string theory and higher dimensional physics, one where our universe isn't the product of a single point of origin, but of the collision between two four-dimensional brains. Brain cosmology, an extension of string theory, suggests that the universe might be a three-dimensional brain, short for membrane, floating in a four-dimensional space known as the bulk. Imagine our world as a vast, dark sheet of space stretched out in a cosmic dimension, with other sheets of space nearby. In the ekpyrotic model, there's at least one other brain that runs parallel to ours, separated from it by an extra spatial dimension. This extra dimension is so tiny that we can't perceive it, but it's there. It's possible that this other brain has its own world, its own physical laws, and its own kind of space and time. After that, it moves. The two brains move toward each other over very long periods, drawn together by gravity or quantum effects. When they collide, their kinetic energy is converted into matter and radiation, which is what we see as the Big Bang. The key is that this model doesn't start with a singularity. There's no point of infinite density. The Big Bang is now just a transition, a moment of extreme energy release caused by a brain collision. The universe doesn't just appear out of nowhere. It grows from a pre-existing structure that has been preparing for its next move. After the collision, the brains bounce apart. As in standard cosmology, the energy dissipates, space expands, and galaxies form. But eventually the brains slow down, reverse direction, and start to move back toward each other. This leads to another collision, a new universe, and another Big Bang. This cycle could be endless. This is the cyclic model of the ekpyrotic universe, which proposes that the cosmos is born, reborn, and reborn again. Each cycle could last up to a quadrillion years. After each bang, everything starts over, with new physics, new stars, and maybe even new kinds of life. The universe stops being a linear story and instead takes on a dynamic, living rhythm. One of the strongest reasons for the ekpyrotic model is that it offers solutions to deep cosmological puzzles. The flatness problem, why is the geometry of space so close to perfectly flat? The horizon problem, why does the universe look so uniform even in regions that couldn't have communicated with each other? And the singularity problem, how can physics explain a beginning from nothing if singularities break all known laws? While eternal inflation solves these issues by proposing an exponential expansion that smooths things out, the ekpyrotic model takes a different approach. It suggests that the slow ordered contraction that happens before a brain collision can create conditions that are smooth, flat, and uniform, naturally leading to a universe like ours. There's no need for an inflationary blast. It gets even more exciting with the physics involved. This model incorporates 11-dimensional space, quantum fields, and the behavior of brains because it's connected to M-theory, one of the leading candidates for unifying quantum physics and general relativity. This theory suggests that each brain is like a blank canvas on which a universe can paint itself. There's energy and fields in the space between brains, which can influence the outcome of each new cosmic cycle. Now, what would it mean to exist between brain collisions? From a physical standpoint, we might experience little difference. Life on Earth, galaxies, and cosmic structures would form and evolve just as they do in standard cosmology. But over immense timescales, the universe would begin to stop expanding, and gently contract. The stars would die out, space would become cold and dark, and then, deep in this dark epoch, the brains would once again come together. Bang! A new universe, fresh, hot, and teeming with possibilities. For me, the most interesting thing about the ekpyrotic model is that it makes predictions that are different from inflation. For instance, It predicts that the gravitational wave background, the deep hum of the early universe, should be much quieter than what inflation predicts. It also suggests small trends in the temperature variations of the cosmic microwave background, CMB, which might differentiate it from other models. These predictions could be proven or disproven by future experiments, such as those that measure the CMB or gravitational waves with greater accuracy. Many ancient beliefs, from Hinduism's breathing Brahman to the Stoics' concept of eternal return, are deeply connected to the idea that the universe is eternal, cyclical, and renewing. It changes how we think about cosmic death, not as an end, but as a beginning in disguise. From this perspective, the edge of the universe is neither a physical limit nor the end of time. It's the boundary between cycles, the line between eons. If you could stand on the edge of two brain collisions, you would be in the middle of two different times, witnessing one world end and another begin, quantum tunneling into new realms. Imagine you're standing at the edge of everything, time, space, and energy. Then, suddenly, you feel as though you're no longer there. You weren't erased or destroyed, but overwritten, not ending, but beginning somewhere else. This is the reality that quantum tunneling on a cosmic scale describes. It's a strange and perplexing phenomenon that allows particles to cross barriers they shouldn't be able to, defying classical laws as if guided by secret probabilities. Now, apply that concept to the entire universe. At the quantum level, particles don't behave like billiard balls on a table. They don't have a definite location. They exist in a haze of possibilities. Particles can sometimes appear on the other side of an energy barrier when everything else seems to say it's impossible. This is called quantum tunneling. It's how the sun burns, how radioactive material decays, and how life itself progresses, one highly improbable atomic leap at a time. Now, scale that up. What if the universe itself could tunnel, not through space, but through states of reality? Some physicists believe that what we perceive as our universe, with its familiar laws of physics, constants, particles, and forces, is just one configuration in a vast landscape of possible universes. In string theory, this is referred to as the string landscape, a nearly infinite array of vacuum states, each with its own set of physical laws. Our universe, then, is like a marble resting in one valley among many peaks and troughs. According to quantum field theory, the vacuum isn't truly empty. It's a seething, fluctuating sea of energy and potential. And in this sea, it's possible for a region of space to suddenly tunnel from one vacuum state to another, from a false vacuum, a local minimum, to a true vacuum, a lower energy state. It's the cosmic equivalent of the ground beneath our feet, suddenly giving way, not into a hole, but into another kind of existence entirely. This event is called vacuum decay, and while it sounds apocalyptic, it's fundamentally a shift in the fabric of the universe itself. The bubble of the true vacuum would expand at the speed of light, replacing the old vacuum and everything within it with a new one. The laws of physics, the constants of nature, even the number of dimensions could change. Space and time might reconfigure. Matter could be erased or reshaped. If quantum tunneling between vacuum states is real, then the idea of the universe's edge is more like a membrane between different worlds. We could be just one bubble in a vast froth of realities, each one born from a quantum fluctuation and separated by boundaries we can never cross, unless the universe itself changes the rules. This has many implications. It means, among other things, that the universe is metastable. It's not at the lowest possible energy level, but it's stable enough for now. However, quantum physics suggests that tunneling could occur if there's enough time. This isn't science fiction. It's a real projection based on our knowledge of astronomy and field theory. Based on the Higgs field and the known masses of fundamental particles, some scientists even think we can estimate the likelihood of such an event happening. If a vacuum decay occurred, the bubble of new reality would expand at light speed. There would be no warning, no time to observe, no time to react. It would be, in every meaningful sense, instantaneous. But rather than being a cold end, it might be the beginning of something else. Inside the bubble, a new universe could emerge, one with different laws, different constants, and maybe even different forms of matter or life. So what lies outside the edge of the universe? Maybe it's not just space, maybe it's probability, a rolling die of quantum outcomes, where entire universes shift, blink, and shimmer into being. Maybe we live on a ledge of potential, perched between one vacuum and another, oblivious to the invisible thresholds all around us. This makes me think of a multiverse that's both scary and beautiful. It's not made up of different spaces, but of options that are close together, like musical notes ready to be played. If quantum tunneling is real in the universe, then the edge of the universe isn't a wall or a blank space. It's a gateway to other worlds, not traveled with ships or probes, but with time and chance. Even more interestingly, some ideas suggest that tunneling might not only fill empty space, but could also create new bubbles. This is similar to the idea behind eternal inflation, which proposes that every tunneling event creates a new world, each bubble growing and changing on its own. This is the bubble we live in. There could be a vast number more, separated not by space, but by energy state and causality. What if our own universe was born this way? In this view, the Big Bang wasn't the beginning of everything, but merely the birth of our particular vacuum bubble, emerging from a parent state through quantum tunneling. We didn't arise from nothing, but from a higher energy realm that spilled into being, cooled, and formed everything we see. And what about the edges of this bubble? They're unreachable. They expand at light speed, just like the outer limits of our observable universe. But unlike the edge of a balloon that we could someday catch up with, these edges aren't physical locations. They're the transition zone between two distinct realities. The outside isn't space we can reach, but a different physics altogether. But it does bring up an interesting question. Could we ever detect the faint sound of tunneling? Could we see the mark of a vacuum bubble colliding with another? It could be in the form of faint scars on the cosmic microwave background or strange changes in energy and shape. There are experts who think it's possible. They've been looking for clues like hints of curvature, unexplained cold spots, and sudden changes in temperature or density. The door is still open, even though nothing solid has been found yet. Some of the most important things in the universe remain hidden until we're ready to ask the right questions. And even if we never witness the tunneling happen, its implications linger. They whisper of a cosmos in flux, a reality where what exists is only temporary, a fleeting chapter in a much larger book. Quantum tunneling isn't just a quirk of particles. It may be the engine of cosmic renewal, the spark that lights new realms when old ones fall away. Dark flow. Even though it's not something we can see or touch with our instruments, there's something out there that pulls on our universe, like a secret current beneath a vast ocean. This unseen force is called dark flow, and its existence is still hotly debated. However, it's one of the most tantalizing signs that there might be something bigger, stranger, and completely unexpected beyond what we can see. The story begins with the cosmic microwave background, CMB, the ancient faint afterglow of the Big Bang. This radiation stretches across the sky and acts like a photograph of the universe when it was just 380,000 years old. It's nearly uniform in every direction, but with slight variations, temperature fluctuations, and hot or cold spots that provide clues about the large-scale structure of the cosmos. Let's say you're a scientist mapping this background in space with satellites like WMAP or Planck. You notice that galaxy clusters, which are huge groups of matter holding hundreds or even thousands of galaxies, are not moving in the way you would expect. They're not just moving randomly. No matter where they all seem to be moving at the same speed, up to 600 to 1,000 km/s, toward a specific area of the sky. There's nothing in the visible universe that aligns with this trend. It's not like the gravitational pull of other superclusters that we know of. When you look at it on a cosmic scale, it looks like space itself is being pulled by something beyond the cosmic limit. This is dark flow. The term was coined by scientists attempting to explain why these galaxy clusters appeared to be streaming toward a patch of sky in the direction of the constellation Centaurus. The measurements were based on a technique involving the Sunyaev-Zeldovich effect, where photons from the CMB gain energy as they pass through hot gas in galaxy clusters. By studying these subtle shifts, astronomers could estimate the velocity of these clusters, and what they found didn't fit with the standard model of cosmology. The idea is simple but startling. Massive structures that exist outside our observable universe might be exerting a gravitational influence on the regions we can see. If true, that would mean our observable universe, the 93 billion light-year across sphere that we can currently detect, is just a bubble in a vastly larger reality, and that immense concentrations of mass reside beyond our horizon, dragging entire galactic neighborhoods in their direction. Take a moment to think about that. Superstructures, which are impossibly huge groups of matter that could be whole other worlds, might be pulling on ours, even though we can't see or touch them. The subtle movements of matter on cosmic scales may give us a hint of their presence, but not all scientists agree. People have looked closely at the idea of dark flow. Some experts say the data might be flawed or the result is not statistically significant. Later searches with the Planck telescope didn't find the same signal that the WMAP data had shown. This caused a split in the scientific community. One group believes dark flow is evidence of physics beyond the standard model, possibly proof of a multiverse or higher dimensional gravity. The other group believes it's just a measurement error, a cosmic mirage caused by noise or incorrect interpretation. It forces us to confront the possibility that gravitational information isn't constrained by the speed of light in the same way electromagnetic signals are. Gravity propagates at light speed, yes, but if something truly enormous lies beyond our cosmic edge, its gravitational influence may still be felt across the ages. In that sense, gravity becomes a kind of messenger from the unknown, whispering of the unseen in a way that starlight cannot. The anisotropies in the cosmic microwave background, including the axis of evil, a strange alignment in the large-scale structure of the CMB, suggest that something outside our observable bubble might be shaping the internal patterns of our universe. Dark flow, if real, would fit into this family of anomalies, clues to a deeper truth scratched onto the sky by an unseen hand. In some inflationary multiverse models, bubble universes can collide with each other, and their effects could spread through each other like waves merging in a cosmic pond. This kind of collision might leave scars, gravitational shears, flows of matter, and patterns in the CMB that don't follow random statistical noise. In this case, dark flow wouldn't just be a hint at another universe, it might be direct proof of our universe colliding with another, like tectonic plates grinding in the void. The boundary between universes could create strange effects, changing the path of matter on scales that are too vast to comprehend. But we must tread carefully. The observable universe is the largest thing we can study directly. Everything beyond that is inference, speculation, and extrapolation. And yet, science thrives in the realm of the inferred. Every theory begins with a mystery. Every breakthrough starts with a question. Why is that moving like that? And the question, why are these clusters moving together toward a place that can't be seen, is still open. Dark flow shows us that the universe is more than just very large. It could be the pull of unknown giant structures, the whisper of another universe, or a mirage written into our measurements. It's not settled, and the lines we draw between what we know and what we don't, what is real and what is imagined, are often much thinner than we think. The cold spot enigma. High above us, in the faint glow of the early universe, there's a puzzle so small that it was almost overlooked. It's also so perplexing that it continues to challenge our most trusted models of the universe. This strange area in the cosmic microwave background, CMB, is called the cold spot. It covers a huge area of the sky in the constellation Eridanus and is surprisingly cold. But this isn't just an interesting piece of astrophysics. It could be the mark of something from another world. Before we can understand the importance of this mystery, we need to know what the CMB is. When we look up at the microwave sky, we see radiation that dates from about 380,000 years after the Big Bang. This is when the universe cooled enough for atoms to form, allowing photons to travel freely from then on. This light has been traveling slowly, its wavelength stretched and reddened as space expands. These days it paints the sky with almost perfect uniformity, a kind of cosmic wallpaper with tiny temperature variations that reveal how galaxies grow. In 2004, astronomers using NASA's Wilkinson Microwave Anisotropy Probe, WMAP, noticed a strange feature, a large region roughly 5 to 10 degrees across that was significantly colder than expected. This cold spot wasn't just slightly off, it was anomalously low in temperature compared to its surroundings. Later, the Planck satellite confirmed it. The data wasn't a fluke. There really is a patch of the sky that defies statistical expectations. So, what could cause it? The first idea was quite reasonable. Maybe the cold spot was a supervoid, a huge area of space with much less matter than usual. On a very large scale, galaxies are arranged in webs of filaments, clusters, and empty spaces. The integrated Sachs-Wolf effect is a gravitational redshifting process that can happen to light moving through these voids. This is where the curvature of spacetime changes the energy of photons in very small ways. If there is a supervoid, this effect might cause CMB photons to lose energy, making them appear colder when they reach us. This explanation held promise. In 2015, observations using the Dark Energy Survey suggested that a vast underdense region, hundreds of millions of light-years across, could exist in the cold spot's direction. But further studies cast doubt. The void wasn't quite large enough. The temperature difference of the cold spot was too extreme. Statistically, it remained an outlier, something not easily explained by current structure formation models. As a result, the cold spot went from being a normal, if rare, event to a cosmic puzzle. A theory that's gaining more attention is that the cold spot might be a scar from a collision between bubble universes in a multiverse. Some models of inflation suggest that our universe is just one bubble in a foam of space that is perpetually expanding. These bubbles might sometimes collide with each other like soap bubbles in a sink. If that happened very early in the universe's past, the impact might have left a mark on the CMB, either by changing its temperature or shape. The cold spot could be such an imprint, a ghost of another world that briefly crossed paths with ours before drifting away, out of reach, but never truly gone. A different universe with different physical laws may have touched ours at some point in the very distant past. The other universe is beyond our causal reach, so we wouldn't be able to see it directly. However, we might be able to pick up the aftershock in the cosmic microwave background, a small area of cold, an itch in the grand cosmic picture. This scenario may seem impossible, but it fits easily with ideas like eternal inflation, which proposes that space keeps expanding forever in some places, while pocket universes form and solidify from time to time. Fundamental constants may have different values in each pocket. Some may not support matter, while others might host life. From this point of view, the cold spot isn't just a chance dip in temperature, it's a warning from beyond the stars, written in the light from the Big Bang. But let's step back. The cold spot remains controversial. Some scientists caution against leaping to exotic conclusions. Our universe is big, really big, and rare things do happen in large datasets. Even if the probability of such a cold region is low, it might just be cosmic variance, a statistical fluke, a roll of the dice in the cosmic lottery. Could there be other, subtler anomalies like it? Clues sprinkled across the CMB that point to physics beyond the standard model? Some researchers are now using machine learning to search for patterns in the background noise, looking for other hints of bubble collisions or topological defects. Others are scanning for non-Gaussianities, deviations from the expected statistical distribution in the CMB, which might signal the presence of new physics. Philosophers and cosmologists are both thinking about what this means. If the cold spot is a multiverse bruise, what does that imply for our universe's place in the grand scheme of things? Is our world just one of many that float through an endless sea of possibilities? Do the cold spots make us think that we're not alone, not just in life, but in existence itself? But maybe the cold spot isn't a structure in space, but a structure in our ideas, a hole in the way we think about how the universe began. It could be a sign that inflationary theory is flawed, or that our understanding of quantum gravity is incomplete. One thing is certain, the cold spot persists. It has not been dismissed or fully explained. The radio sky is empty and quiet, as if it doesn't want us to try to understand it. It makes us question what we think we know and asks us to imagine what we don't. A message from the edge of our understanding. Unobservable galaxies. We can see galaxies everywhere in the universe. Each one is a vast city made up of stars, gas, dust, and dark matter, spread out like bright islands across the cosmos. There are hundreds of billions of galaxies that we can see, and each one contains billions of stars. But what we see may not even be a small fraction of what is out there. Galaxies that we cannot see drift through space, forever hidden by time and distance. The reason for their invisibility lies in one fundamental limitation. Light has a speed limit, and the universe has an age. But beyond this bubble, there may be vast realms of galaxies we will never see, not now, not ever. These are not hypothetical galaxies. They are as real as the Milky Way. They could contain stars just like our Sun, planets just like Earth, and even intelligent life pondering the cosmos just as we do. But the space between us and them is expanding faster than light can travel. As a result, their light will never reach us. These galaxies have slipped over our cosmic horizon, a line drawn not in space but in time. This limit is also not set in stone. With each second that passes, light from slightly farther away reaches us. As our knowledge of the universe grows, so does the space between us and those receding galaxies. In fact, the number of galaxies we can see will decrease in the far future because the universe is expanding faster than ever. This is caused by something we term dark energy. It's like being on a vast plain and seeing campfires in the distance. At first, as the smoke clears, more and more become visible, but over time, those campfires start to extinguish and disappear into the night, driven away by a wind you can't see. On a grand scale, that is what's happening. How many galaxies are out there beyond our sight? The Hubble Space Telescope, and more recently the James Webb Space Telescope, JWST, have provided astonishingly deep field images of tiny patches of sky, revealing thousands of galaxies in areas no bigger than a grain of sand held at arm's length. By extrapolating these deep field counts across the sky, astronomers estimate the observable universe contains around 2 trillion galaxies. But that's just the visible slice. Many astrophysicists suspect the total number of galaxies, including those we will never observe, may be infinite, or at the very least so vast as to be effectively uncountable. Some models suggest that the unobservable universe could be hundreds or even thousands of times larger than what we can see. If true, then for every galaxy we know, there may be hundreds or thousands more floating in unreachable realms. Do the laws of physics apply to both? We think that the unobservable universe should follow the same physical laws as ours, since they both originated from the same Big Bang. But if we consider inflationary multiverse models, some of those galaxies might exist in different bubbles of the universe, where the laws of physics are different. These bubbles could have different levels of gravity, particle masses, and even numbers of dimensions. This has very important effects. There may be galaxies out there that we can't see where the stars are not made of hydrogen and helium, but of strange particles. There may be places where gravity is slightly stronger, which would make stars burn out faster and galaxies fall apart more quickly. Some places might not even be habitable for life as we know it. On the other hand, there may be galaxies remarkably like our own, complete with spiral arms, supernova, planetary systems, and perhaps civilizations. Could those civilizations ever know of us? Almost certainly not. The gap between us grows faster than light can close it. We are, in a very real sense, cut off. This isolation may seem tragic, but it's also awe-inspiring. In every direction, just past the edge of the observable, are countless worlds we will never meet, and skies we will never map. The cosmic darkness isn't empty. It's overflowing with hidden complexity. And just as there are galaxies that can't be seen, many other galaxies can't see us either. Observers in a universe that is expanding as quickly as ours have their own cosmic boundary, their own small piece of the universe. We live in one of these slices. For a being in a world 50 billion light-years away, we might already be too far away to reach, even in theory. In a very deep way, this makes you humble. At first glance, our part of the universe seems very large and full of things, but it could only be a small piece in a much bigger and more complicated puzzle that we can't even begin to piece together with our tools. Some scientists are hoping that future studies will give us hints about these hidden galaxies. It's possible that gravitational waves, cosmic neutrino backgrounds, or small changes in the rates of expansion will tell stories from the edge of what we can see. One day, maybe we'll be able to see the total gravitational mark of galaxies that we can't see by how they pull on things we can see, but for now, all we can do is guess and infer. That may be why they're so powerful. The galaxies that can't be seen are not only far away and dark, but they are also the very essence of wonder. They tell us that we're not here to conquer the universe, but to be humbled and amazed by it, that there are more stars, stories, and questions behind every part of the night sky. The unknown mass is made up of them. Those are the galaxies, past the edge. Even though we'll never reach them, they change the way we see the universe, not by shining light on it, but by simply being there. The limits of cosmic light is our window to the universe. Every galaxy, star, and planet we know because of light. It travels across space and time to carry ancient messages from distant corners of the cosmos, revealing the history of stars, the birth of galaxies, and even the echoes of the Big Bang itself. But light, as miraculous as it is, has its limits. And those limits define the edges of what we can ever hope to see. To understand what exists outside the edge of the universe, we must first understand the limitations of light, because our entire view of the universe is ultimately constrained by how far and how fast light can travel. The first and perhaps most famous limit is the cosmic microwave background, CMB, the oldest light we can see. It comes from about 380,000 years after the Big Bang, a time when the universe had cooled enough for electrons and protons to combine into neutral atoms, allowing photons to travel freely through space. Before that era, the universe was opaque, a blindingly hot plasma that scattered light constantly, much like the inside of a star. This makes the CMB the limit of electromagnetic visibility. No matter how good our telescopes become, no matter how long we wait, we will never see light from before the CMB because no light from that earlier epoch was free to travel. It's like trying to see inside a star by looking at its surface. There's a limit beyond which visibility ends. Cosmologists call the time period after the CMB the cosmic dark ages. It's the time between the last scattering of photons when the CMB was released and the start of star formation. At this point in time, the universe didn't have any light that could be seen or that was close to infrared. It was a vast, dark, and quiet space, full of cool gas and the beginnings of galaxies. The first stars and galaxies were formed when gravity initiated what is called cosmic reionization. This is the process by which starlight lit up the universe again, ending the Dark Ages. The James Webb Space Telescope is designed to look back over 13 billion years to find the first bright objects and study this early period. However, not even it can see into the prestellar darkness before reionization or past the CMB. What happens if we try to go even further back to learn about the first 380,000 years of the universe, or even the first fractions of a second after the Big Bang? We need to use non-electromagnetic messengers. Light won't help us there. We need to use gravitational waves and cosmic neutrinos, which are not limited in the same ways that photons are. Einstein predicted that gravitational waves would exist in spacetime, and they do. In theory, gravitational waves could pass through the hot, dense, early universe where light could not. If we could find primordial gravitational waves, we might be able to see the universe as it was, right after inflation, the idea that it grew exponentially in the first few hundredths of a second. However, these waves are very weak and hard to find, and so far we have only seen them from relatively recent events like black hole mergers. Then there's the cosmic neutrino background, ghostly relics of the Big Bang that decoupled from matter just a second after the universe began. These neutrinos are incredibly abundant, but because they interact so weakly with matter, they are nearly impossible to detect. Still, they're out there, forming a silent, invisible boundary even older than the CMB. If we could learn to see them, we could peel back the curtain of time even further. And here lies the paradox. The earliest moments of the universe are also the most shrouded in darkness. The closer we get to the beginning, the more our traditional observational tools like light break down. The physics of that epoch involves energy scales and conditions that we simply can't reproduce, and in many cases can't yet describe with certainty. Our best models, quantum field theory, general relativity, string theory, strain under the pressure of those early instants. Even worse, dark energy speeds up the expansion of the universe. As we move closer to the edge, even though they are billions of light years away, some galaxies are moving away faster than light. This isn't because the galaxies are moving through space, but because space itself is stretching. So, no matter how long we wait, the light coming from those galaxies today will never reach us. This is not a violation of special relativity. Special relativity forbids objects from moving through space faster than light, but space itself can expand as rapidly as it wants. In fact, more and more of the universe is becoming invisible every second. In the far future, only the galaxies gravitationally bound to us, like those in our local group, will remain visible. The rest will fade away, forever beyond the reach of light. This means that the answer to the question, what is outside the edge of the universe, is constrained by light. There may be no end to the cosmos, but light can only go so far. The edge isn't a wall or a real line, it's the edge of what light can show us. After that, there's darkness. Not empty space, though. There may still be stars burning, galaxies growing, and whole civilizations staring into the night sky without seeing us, just as we don't see them. They are not reachable by photons and can't be traced through light's past. And their light will always be beyond the edge unless we find new ways to see the universe, like using neutrinos, gravitational waves, or information sources we don't yet know about. The boundaries of cosmic light aren't just about science in the end. They're about perspective. They help us remember that what we see is only a small part of the whole, that even though the universe is made of light, there are places where it's dark. This isn't because there's nothing there, but because the light hasn't yet arrived. Is there an anti-universe? The idea of an anti-universe comes from scientists trying to solve some of the biggest puzzles in modern physics, especially those related to symmetry. The concept behind physics is that certain patterns should hold true in both space and time. What does CPT stand for? It stands for charge, parity, and time. If we perform three actions simultaneously, reverse the charge of all particles, turning matter into antimatter, flip their spatial dimensions, creating a mirror image or parity, and reverse the flow of time, the laws of physics should remain the same. Many physics laws follow this CPT symmetry. The fundamental way particles behave doesn't change when you apply all three transformations at the same time. The universe may follow this pattern, but only locally. What about on a larger scale? This is where the anti-universe theory comes in to help explain things. Some cosmologists think that the Big Bang wasn't the beginning of time, but rather a point of change, a moment when everything was perfectly balanced. Our universe, which is expanding forward in time, is on one side of this line. On the other side is a universe that expands backward in time, like a mirror world where antimatter dominates, and all physical processes occur in reverse. This idea isn't just a philosophical musing, it's mathematically grounded in attempts to explain anomalies in particle physics. For instance, we know that our universe contains far more matter than antimatter, a fact that remains one of the great unsolved puzzles of cosmology. Theoretically, the Big Bang should have produced equal amounts of both. So, where did all the antimatter go? One answer is that it didn't go anywhere. It just exists somewhere else, in the anti-universe. This mirror realm wouldn't just have antimatter. It would also have time reversed, which is similar to anti-causality. From our perspective, things would happen there in a way that looks like a timeline going from the future to the past. From that universe's point of view, however, they're moving forward at their own pace. In the same way that we feel chaos rising, they would too, but in the opposite order. It's hard to think about this without running into conflicts. People in the anti-universe would remember the past and look forward to the future, right? How would their physics feel compared to ours? It's possible that the answer is yes. All of their processes, from nuclear fusion to biological growth, would happen concurrently in their world, so their experience would be the same as ours. They wouldn't perceive themselves as moving backward in time at all. They would think we were the weird ones. The most exciting thought is that some cosmic signs might point to the existence of a mirror world like this. Neutrinos, which are ghostly particles that don't interact with matter very often, could be a sign. According to the standard model of physics, neutrinos come in 3 different types, and all of them are left-handed, which means their spin direction is opposite to their direction of motion. This difference in handedness is strange because most particles come in both left and right-handed forms. This imbalance could be fixed by the anti-universe model, which suggests that the right-handed neutrinos, which we have never observed, are actually from the mirror universe, just as the left-handed ones are from ours. If this is true, it would not only solve the symmetry puzzle, but also help us learn more about dark matter, which some scientists think might be composed of these right-handed neutrinos. But what's even more interesting is the idea that our universe and the anti-universe may have both originated from the same event that happened at the same time. The Big Bang isn't a place where physics breaks down. Instead, it's like the center of a bow tie. It's where 2 worlds meet and start moving in different directions in time. From this point of view, time doesn't move in a straight line. What we think of as forward is really just one part of a bigger picture. The anti-universe, which we can't see or reach, may be growing and changing in perfect order, with its own galaxies spreading, stars burning, and maybe even life developing in a place we will never be able to reach. Could we ever detect this anti-universe? Perhaps not directly, but some cosmologists believe that subtle traces of this mirror reality could be hidden in the cosmic microwave background. Tiny anomalies or unexpected patterns in the CMB might be interpreted as echoes of the symmetry across the Big Bang boundary. There is even speculation that certain gravitational waves, ripples in the fabric of spacetime, could carry signatures from both sides of the temporal divide. But these ideas have not been proven yet. The anti-universe is still just a theory, a mathematical possibility that needs to be confirmed by experiments. Our equations look better and are more balanced with this answer, but we don't have direct proof of it yet, so it's still just a guess. If there is such a thing as an anti-universe, then the Big Bang wasn't a unique beginning, but rather a point of birth that is mirror symmetric. We're not the only thing that came from the beginning of the universe. We're only one part of a perfectly balanced system. That being said, we might never trade light or matter with this other universe, but the symmetry could influence neutrinos, dark matter, chaos, and even the direction of time itself. Gravitational waves from beyond in 2015, a wave arrived on Earth. This wave wasn't made of light or sound. It was a gravitational wave, a distortion in the very fabric of space and time. It was the first direct detection of these elusive waves, which were generated when 2 black holes collided more than 1 billion light-years away. This confirmed Einstein's prediction from 100 years prior. Gravitational waves are not composed of particles. They are ripples in spacetime caused by massive objects moving at high speeds, such as neutron stars merging or black holes orbiting each other. While light can be scattered or absorbed, gravitational waves are almost never blocked when they pass through matter. They carry information not about the exterior of cosmic events, but about their very centers. This includes the moments when stars collide, black holes merge, and the structure of space is violently reshaped. Now consider this. If gravitational waves can reach us from such violent collisions, could they also bring signs from other universes that we can't see? This is what some experts think. If there are huge structures or events in the universe beyond our cosmic horizon, the edge set by how far light has traveled since the Big Bang, those phenomena could still emit gravitational waves. While light from beyond that edge will never reach us, gravitational waves might. There is a small chance that these waves could carry echoes from before recombination, from times when light was still trapped in the plasma of the newborn universe. They might even be from different regions of a larger multiverse. Others think that gravitational waves might travel through or around topological flaws in spacetime, such as cosmic strings or domain walls, if they exist. These ancient remnants of the early universe could shake or break, sending gravitational signals over very long distances, perhaps from worlds other than our own. If we could detect these very low-frequency waves, they might give us our first glimpse of what lies beyond the edge of what we can see in the universe. Of course, detection is the hard part. We can barely hear gravitational waves now. LIGO was needed to record waves from within our own cosmic neighborhood because it can detect distortions smaller than the width of a proton. To hear sounds from beyond, we would need even more sensitive instruments, like the planned Laser Interferometer Space Antenna, LISA, in space, or perhaps even entirely new technologies we haven't yet conceived. The edge, according to general relativity. In real life, physics works the way we see it. We stay on the ground thanks to gravity, time moves forward, and space appears to go on forever. But physics breaks down at the most extreme points of reality, like the center of a black hole or the moment the Big Bang happened. In particular, Einstein's beautiful theory of general relativity, which has been our guide for over a century, starts to fall apart. In general relativity, gravity isn't seen as a force, but as the way that mass and energy bend space-time. It's what makes light bend around galaxies and planets orbit stars. It predicts that time will slow down near very massive objects, that the universe will expand, and even that black holes will form. But the equations don't make sense at the edges of these phenomena, which are called singularities. A singularity is a point where density becomes infinite and the curvature of spacetime grows without bound. This isn't just a mathematical oddity, it signals the limits of our current understanding. General relativity can't handle infinities. It can't describe what happens at the singularity, only what happens approaching it. And that's crucial, because if the universe has an edge, spatially, temporally, or conceptually, it may resemble such a singularity. Consider the Big Bang. We often picture it as a massive explosion from a central point. But that's misleading. The Big Bang wasn't an explosion in space. It was an expansion of space. What existed before it? General relativity has no answer. Its equations simply say, here lies a singularity, a beginning point where time and space as we understand them emerge. But why? From what? That is where relativity stops. Similarly, general relativity predicts that there will be a point inside a black hole, past the event horizon, where space-time collapses into a singularity. But it doesn't say anything about what is there. Is it a pinpoint with infinitely high density, a hole that leads to another world, a gateway to another universe? Our tools don't work in that region, so no one knows. Physicists believe that to truly understand the edges, the places where general relativity breaks down, we need a theory of quantum gravity, one that unites the smooth geometry of Einstein with the probabilistic nature of quantum mechanics. String theory, loop quantum gravity, and other candidates are attempting to bridge this gap, but none have succeeded definitively. Until then, the edges remain just out of reach. They are like a cosmic shoreline shrouded in mist, where the laws of physics we trust dissolve into paradox. General relativity is one of humanity's greatest achievements, but it leaves us with tantalizing questions. What lies beyond its domain? If the universe has an edge, perhaps it's not spatial but epistemological, a boundary not of matter but of understanding. The cosmic neutrino background. Before the first stars were born, and even before atoms were made, the universe was a sea of particles on fire. It was so hot and dense that light couldn't escape. Another type of particle, neutrinos, was born and set free at this time. These ghostly particles, which have almost no mass and don't interact with anything much, slipped through the chaos and started their journey through space. They may hold secrets from the very beginning of time, even before light existed. The cosmic neutrino background, CNB, is a piece of history from the second after the Big Bang. That's about 380,000 years before the photons of the cosmic microwave background, CMB, were released. This means that the CMB could be a way to see a time that photons can't show. But finding these ancient neutrinos is like trying to hear a whisper in a storm. They don't interact with matter much. Every second, trillions of them pass through planets, stars, and us. Because the universe is expanding, the CNB has very little energy, making it even harder to find. Its neutrinos are colder and move more slowly than most we see. Current detectors work by observing high-energy neutrino interactions, so they can't see them yet. Still, scientists are coming up with new ways to hear this very faint hum. The Princeton Tritium Observatory for Light, Early Universe, Massive Neutrino Yield, Ptolemy, and other experiments try to find relic neutrinos by studying how they interact with tritium atoms in very small ways. If we're successful, we might be able to prove one of the last untested ideas about the Big Bang and see things that happened before we have ever seen them. The CNB is very interesting because it might be able to tell us about the world before light, before the CMB, and before any matter that we can see. Perhaps it will help us understand how matter and antimatter behaved, or whether unknown physics shaped the early universe. Neutrinos don't interact with anything very strongly, so they move through space and time almost unchanged. They are like messages from the beginning of the world. Assuming there was a before the Big Bang, some experts even think that leftover neutrinos might carry marks from that time. If the universe came from a cycle or a quantum shift in the past, these very small particles may still have signs of those events on them. The CMB is one of the most important targets in current astronomy, even though it's only a theory. Time before time, what was there before the Big Bang? For many years, this question was considered pointless, the final word in astronomy. We were told that the Big Bang was the beginning of time itself. To ask what came before was like asking what lies north of the North Pole. Modern theoretical physics, on the other hand, doesn't like dead ends. The idea of a time before time has been brought up in serious scientific conversations recently. This cutting-edge idea questions the very basis of causality and the history of the universe. Classical general relativity says that the Big Bang is a singularity, a place where space and time become so dense that the known rules of physics no longer apply. But these days, most scientists think that this singularity isn't a real thing, but rather a sign that we don't fully understand quantum gravity and where it should take over. In some theories of quantum cosmology, time doesn't start with the Big Bang. It just changes over time. The Harlow-Hawking no-boundary proposal is one of these ideas. In this plan, time is seen as a dimension that changes into space-like properties, near the beginning of the universe. The universe doesn't have a clear start in this model. Instead, it ends in a curve that looks like the top of a dome. It doesn't have any sides, a hollow spot, or a real beginning. It's like a disk that slowly forms, with time moving from a quantum beginning that has no direction. Then there are the bounce models, which are possible futures in which the universe shrank in the past and then grew again. From these points of view, the Big Bang happened after a big crunch. There was no beginning of time 13.8 billion years ago. It either went backward or forward during a transitional period guided by quantum rules we don't fully understand yet. In theory, these cycles could go on forever, creating a universe that is always being born again and again, where time before the Big Bang is just time moving from one phase to the next. Some studies even say that time might not be fundamental, but rather emergent. You could say that time could come from more basic quantum interactions, like how temperature comes from the movements of molecules. According to these ideas, time might not flow the way we think it does after a certain point in the history of the universe. This means that there might be a place before time where things don't work the way we think they do. Not only does the idea of time before time push the limits of science, but it also changes them. It makes us think that our origin story isn't the beginning, but rather a chapter in something stranger, more circular, or more quantum than we thought. There might not be a void before the first tick of the universal clock. Instead, there might be a veil that new physics will one day lift. Exotic topologies. Most of us think of the universe as an endless grid, a three-dimensional stage that's always getting bigger, where galaxies move apart, stars shine, and space itself grows. What if, though, the shape of the universe is much stranger than we think? Welcome to the world of exotic topologies, where space doesn't behave in a way that makes sense. In these models, the universe could loop, twist, fold, or wrap in ways that don't make sense in the real world. This would not only create new forms, but also new possibilities for what lies beyond the edge. First, let's look at the torus universe, which is already pretty strange, but has a lot of math behind it. Think about how the universe looks like a big donut. In this kind of place, if you go far enough in one direction, you'll end up back where you started, without ever turning around. This place doesn't have any edges. It's like the surface of a sphere, but in 3 dimensions. With this idea, beyond the edge is rethought as a structure with loops. You don't reach a wall, you complete a cosmic lap. Then come even more curious constructs: Mobius strips, Klein bottles, and projective spaces. These are mathematical shapes where direction, orientation, and movement take on non-intuitive meanings. A Mobius strip has only one side and one edge. A Klein bottle, if extended to 3 dimensions, loops back through itself in a way that defies normal spatial logic. Applied to cosmology, such models suggest a universe where left and right might subtly blur, or where traveling up could gradually reorient you down. These are not merely thought experiments. They are geometries consistent with Einstein's theory of general relativity, given the right conditions. Hyperbolic geometries take things further still. In these models, space is curved in such a way that it spreads outward faster than flat space, creating infinite volume within finite bounds. Picture an endlessly branching coral reef, or a tree that sprouts new branches faster than light can cross them. In a hyperbolic universe, light rays that leave your position never reconverge, creating pockets of isolation and vast voids that mimic the structure of our own cosmic web. What is the point of these strange topologies? Because they change what the edge means. If the universe curves, folds, or loops, then outside might just be a way to get back inside. The real limit might not be in space, but in structure, like a geometric cutoff that we don't know how to cross yet. It also means that two seemingly separate parts of the universe could be the same area, linked by a wavy structure, like two ends of a folded piece of paper being taped together behind the scenes. There is also the intriguing chance that cosmic illusions are caused by strange layouts. The cold spot, repeated galaxies, or unexplained patterns in the cosmic microwave background could be signs of a universe that folds or loops in ways we haven't yet discovered. If that's the case, the edge of the universe might be right behind you, bent by space. Wormholes and exits. At its core, a wormhole is a bridge. Einstein's field equations allow for a tunnel-like solution in spacetime. If you fold a piece of paper in half and then poke a pencil through it, the pencil moves straight through the paper instead of across it. This is the idea of a way to cut through space-time faster than usual, avoiding normal distances and possibly connecting places that are light years or even worlds apart. When it comes down to it, wormholes can be either intra-universal, within our own universe, or inter-universal, between worlds. Wormholes could lead to places far beyond the visible universe or to worlds with completely different laws of physics if they exist and are stable enough. This puts them right in the category of exits, not just past the edge of what we can see, but past the edge of everything we think of as here. The Einstein-Rosen bridge, which is the simplest type of wormhole that can be made from black hole math, isn't stable enough to pass through. It falls apart too quickly for anything to get through. Theoretical physics says that we would need exotic matter with negative energy density to keep a wormhole stable. This is matter that doesn't follow the known rules of energy conservation. Small amounts of negative energy might be possible, as shown by quantum effects like the Casimir effect, but how this would work on a larger scale is still very much unknown. Then there's the matter of causality. If there are wormholes that can join 2 points in space or even in time, do paradoxes make sense? For example, could you emerge from a tunnel before you went into it? The chronology protection conjecture is a theory that some scientists say quantum effects might self-correct to prevent time travel problems. Still others think wormholes might work more like one-way gates, where once you go through them, you can't come back out. An exit, yes, but not a return trip. People have also suggested that black holes could be one-way wormholes. Would you be able to get to the center without becoming spaghettified? If not, could you come out somewhere else, or even at a different time? Some ways of thinking about spinning black holes, Kerr black holes, imply this, with solutions that point to structures inside them that lead to other universes. But once more, these are still very much guesswork and probably can't be crossed by any known material. Quantum wormholes are very small, short-lived links at the Planck scale. They may exist in a boiling foam of space-time. Even if real wormholes can't be traveled through, in theory, these mini wormholes could carry quantum information, pointing to a web of connections we can't see. Beyond the horizon, could the universe be made of secret shortcuts that change its structure without anyone knowing? If wormholes exist, and if we ever discover how to harness them, then the edge of our universe might not be a boundary, but a door. The universe as a simulation. What if the edge of the universe isn't a physical barrier, but a programmatic limit. What if everything, space, time, matter, consciousness, is unfolding inside something far more artificial than we imagine? Welcome to the provocative hypothesis that the universe may be a simulation. This idea, while speculative, has grown in popularity among physicists, philosophers, and tech thinkers alike. At its core is a simple question. If it's possible to simulate a universe, and civilizations can create countless such simulations, then how do we know we're not inside one? Philosopher Nick Bostrom laid out the argument in 2003, suggesting that at least one of the following must be true. Just like in video games where only the visible world is rendered, perhaps the universe generates detail only where and when it's observed. This would mean the unobservable universe isn't out there until we look or try to. The simulation may have limits, and those limits could coincide with the cosmic horizon, where light hasn't had time to reach us. Beyond that, not rendered, not needed. Some scientists have looked for glitches, small mistakes in the universe's code. It's possible that space might be broken up into pixels at the smallest scales, creating a digital grid instead of a smooth line. Others think that high-energy cosmic rays might show anisotropies, preferred directions in space, which could point to a computing base. There's also the quantum observer effect, which says that particles only choose a state when they're being watched. Could this be a type of planned strategy that changes reality based on how people interact with it? That would make every conscious experience a part of the user interface, UI, of the game. Yes, it's a lot to consider, but quantum physics already feels like software whose source code we can't quite read. In a simulated universe, the idea of an outside becomes radically different. Outside isn't more space, it's the higher dimensional reality where the simulation is running. The beings in that world, our programmers perhaps, would exist beyond everything we know, and their rules, motives, or physics may have no correlation to ours. Even time as we experience it may be a setting rather than a constant. Could we ever escape the simulation? Probably not in any traditional sense. But some thinkers propose that anomalous events, unexplainable coincidences, or sudden shifts in physical laws might hint at code changes, patches, so to speak. And in such a framework, asking what lies beyond the universe is akin to a character in a video game asking what is beyond the screen. Hidden higher dimensions. As you walk through your house, imagine finding a secret staircase hidden behind a bookcase. This staircase leads to a place you didn't know existed. Now picture this happening in space instead of your house. This is the crazy idea behind secret higher dimensions. There are realities all around us that are hidden so well that we can't see them. String theory and other similar models of fundamental physics say that the world is bigger than the three dimensions of space and one of time that we see every day. Instead, these ideas suggest 10 or even 11 dimensions, with the extra spatial dimensions being compactified or curled up so small that we can't see them. Calabi-Yau manifolds are complicated mathematical structures that are often used to show these squished dimensions. These are multi-dimensional geometric shapes that may be the building blocks of the particles and forces in our world. What does this mean for the universe's edge? Well, if these hidden dimensions are real, then the outside of the world we can see might not be in more space, but in places we can't go. Even more than not being able to go beyond the cosmic horizon, there may be whole ranges of directions where we physically can't move. This is because our world is only a 3D slice of a much deeper reality. In this view, the universe could be like a sheet of paper floating in a vast, higher dimensional space. We, the beings on the sheet, can move left, right, forward, or back, but never up or down into the larger space. And yet, that space may be real. If we could somehow access it through a wormhole or a fluctuation in the fabric of spacetime, we might discover that the edge of the universe isn't an end, but a fold. And on the other side, who knows? Perhaps another universe or a completely different realm of physics. Gravitational forces have been used in some studies to look for proof of higher dimensions. One idea for why gravity is weaker than the other fundamental forces is that it leaks into other dimensions. Experiments like the Large Hadron Collider have looked for signs of this kind of leaking, like missing energy or particles that behave in unexpected ways, but so far, nothing conclusive has been found. If these extra dimensions are real, they might have something to do with how the world was formed and how the natural laws we observe work. They might even be able to bring general relativity and quantum mechanics together, which is the great grail of modern physics. It's possible that these higher dimensions are not just curled up. Some of them could be wide open and link different universes, like roads between worlds. This means that what we think of as outside the universe might just be going sideways in a place we can't point to, but that is real. The big bounce in cosmic recycling. What if the end of the world isn't really the end? What if it's just a breath between all the breathing that will ever happen? The Big Bounce theory says that our universe is just one in a never-ending pattern of birth, death, and rebirth. This is different from the common idea that the universe started with a Big Bang and is now growing all the time. This idea changes the way we think about what might be beyond the edge. The border is no longer a line that marks the end of space or time. It's now a path to another cosmic era. In a big crunch, the universe might fall apart due to its own gravity. Like a phoenix rising from the ashes, it might then explode outward again in a new Big Bang. This universal rebirth could happen over and over again, like a heartbeat that beats through everything. The Big Bounce theory arises from attempts to resolve the paradoxes of the Big Bang using quantum gravity, particularly in a model called loop quantum cosmology. In this framework, space-time is not infinitely divisible, but has a smallest possible unit. When the universe contracts to an extremely dense point, instead of reaching a singularity where physics breaks down, it rebounds. Time doesn't end, it flips. The expansion that follows is a new universe, a new chapter in an eternal book. If this theory is true, then the edge of our universe might be neither far away in space nor long ago in time, but beneath us, in a cosmic layer that came before. Each bounce could bring subtle changes, different constants, forces, or dimensions, meaning that each universe might be similar, but not identical to the last. The idea behind this is that the universe is really just one turn in a much bigger metaverse. Each world rises, spreads out, and then falls back into the deep, just like waves on an endless ocean. The universe takes on a life of its own, breathing and beating to a constant rhythm. Some people even think that the cosmic microwave background might hold clues to past cycles. Roger Penrose and other scientists have come up with models like conformal cyclic cosmology that say weak marks or patterns in the CMB might be the echo of a dying universe. When we ask the Big Bounce, what lies beyond the edge of the universe? It gives us a beautiful answer. We are there before us. We are the recycled universe from the past that will be recycled again. Not a straight line, but a curve that goes on forever. Could life exist beyond our bubble? Could life, intelligent or not, exist in places we will never reach or even see? This is one of the most interesting and depressing questions in science and philosophy. If our universe is just one bubble in a frothy ocean of universes, what kind of weird life might be living in the bubbles next to ours? What crazy ecosystems could form in a world with strange physics, different dimensions, or different laws of time? In the world we can see, life is already limited by very specific conditions. This is known as the Goldilocks zone. It's important for planets to have the right chemical elements, be neither too hot nor too cold, and orbit a star that is mostly stable. These strict rules make life seem very rare, maybe even magical. But in a bigger multiverse with billions of other worlds, each with its own possible version of physics, the range of possibilities could be much wider. In some situations, we might even have to change our ideas about what life means. Could life built on silicon survive in very hot, highly radioactive areas? Could living things be made of pure plasma or patterns of quantum information stored in spacetime itself? Maybe there are intelligent clouds floating through worlds that look like nebulae, or maybe whole civilizations made up of dark matter beings that we can't see or understand. One interesting angle is the idea that the physics rules we know, which seem to work so well for our life, might not work at all for everyone. There is a chance that fundamental factors like gravity, electromagnetic fields, and the strength of nuclear forces would be different in other worlds. It's possible that some combinations would make worlds too unstable for atoms to form, but other combinations could make things more complicated in different ways. There could still be life, but it might not be built on carbon, need water, or be limited by time in any way we can think of. It's interesting that life beyond the bubble doesn't always mean living things flying around in spaceships. It could refer to systems that copy themselves, change over time, and show awareness in totally different environments, life as we don't yet know it. If we can't see or reach what is beyond, why should we care about it? Because it makes people think and ask new questions. It makes us think about how uncommon or normal our lives may be. Not only does it make the world more mysterious, but it also makes us more mysterious as to what we are in the vast range of possibilities. Do other universes have different physics? What if there was no gravity? It's possible that atoms never formed, or if they did, they would act more like jelly than rigid mass. In a lot of multiverse theories, especially those that are based on string theory and eternal inflation, each world may have its own set of physical rules, constants, and structures. That means that some worlds might be very different from ours, not just in what they contain, but also in how they work. The physical rules in our world seem to be steady and apply to everyone. Light always moves at the same speed. It doesn't matter which way you look at it. Electromagnetic fields, space, and time are warped by gravity, and quantum physics dances around the edges of confidence. But these well-known forces might only be the result of the way things were at the start, or of symmetry breaking that happened when the universe cooled down after the Big Bang. If space is like a cosmic landscape of possible energy states, then each bubble universe may settle into its own unique valley, a minimum energy configuration that would determine what kinds of particles exist there, how they interact, and whether matter can form at all. Some universes may collapse immediately after birth, others may stretch and expand like ours, but with different building blocks of reality. In a world with a less strong nuclear force, atomic nuclei wouldn't be able to form, and science as we know it wouldn't exist. Or what if protons were lighter than electrons? There would have been no stars, planets, or life. It's amazing how well our world is tuned. In fact, some scientists think that the only way to understand it is by using the multiverse. We live in a world that just so happens to be right for life because in many other universes, life isn't even a possibility. But these strange worlds might not be empty all the time. If time moves differently, or gravity acts repellently instead of attractively, you could think that order, stability, and even awareness would appear in ways that we have never seen before. Some ideas say that quantum tunneling might let universes hop between physical rules and experience different configurations for a short time. But the physics behind this is only a guess. It's interesting that this idea of different rules also brings up a philosophical question. Is our world the only real one because we can see it? Or are all physically possible arrangements equally valid, even if they don't create observers? How would we ever know they exist if some worlds have rules that make it illegal to look at them? The thought that physics isn't uniform but unique to each universe is both very scary and weirdly freeing. Is intelligence watching us from beyond? Are we really alone in the universe? Or are we part of a bigger picture that is being watched and maybe even studied by intelligent beings from other universes? This kind of thinking is almost like science fiction, but it makes sense when you think about how big and different multiverse ideas are. One idea, called the cosmic zoo hypothesis, says that Earth and the rest of the world are like an isolated terrarium. They are closed off, contained, and maybe even put there on purpose to keep certain things from getting out. This idea turns the famous Fermi paradox on its head. It's possible that we haven't found alien societies because we're not supposed to. It's not that they don't exist. Now extend that idea from our galaxy or universe to the multiverse. Could there be meta-civilizations, entities so advanced that they exist not within our space-time, but outside or adjacent to it? These beings wouldn't just be aliens in the traditional sense. They might exist across higher dimensions or operate in universes where time and matter follow different rules entirely. The notion isn't completely unfounded in theoretical physics. If our universe is a brain within a higher dimensional bulk, as in brain cosmology, then other brains or universes could be close by. Advanced intelligence might be able to interact across brains, much like a fish might become aware of water currents shaped by a nearby swimmer. We may never see the swimmer, but we feel the ripple. Could these intelligences have engineered our universe? Some theories even propose cosmic natural selection, where universes that are better at creating black holes, and thus potentially spawning more universes, are more fit in a multiversal sense. What if intelligence itself becomes a cosmic reproductive strategy? If such beings exist, they might not only observe our universe, they might have created it. Even though these ideas are interesting, there's no real-world proof to back them up. If there are people who are watching, they haven't said a word. No strange gravity waves, no strange energy patterns, and no peek behind the curtain. Then again, would we know where to look? An intelligent being from outside our world could talk to us through topological changes or quantum fluctuations that we can't see or hear. Some experts are interested in the possibility that this kind of intelligence could use our brains or thoughts as a mirror, with awareness itself tuned to pick up faint signs from other worlds. These are wild ideas, but they do point to something important. Maybe just thinking about the multiverse is a way to connect with other people. If there is intelligence outside of our universe, we might never be able to reach it, but it could be reaching us already in ways we haven't thought of yet. Can signals escape our universe? We don't just see stars when we look up at night, we see signals sent through space and time. Each photon that comes to Earth is a message from the universe. But as we think about what the edge of the universe is like, an even more interesting question comes up. Can any signal get out of our universe? If so, where would it go? Before we can understand this, let's go back to the idea of causal limits. We can only see as far as light has had time to travel since the Big Bang. This means that the world we can observe is limited not by space but by time. The cosmic horizon is that line, and it's getting wider. But what else? In theory, the universe keeps going. What we don't know is if there's a real physical border, or if what is beyond is so disconnected that it can't be reached at all. So, if you aimed a laser pointer into the deepest dark and fired, would it ever leave the universe? The answer depends on what you mean by leave. In standard cosmology, space isn't expanding into anything. It's simply stretching. That means the laser light would keep traveling, but the space between it and everything else would also keep expanding. Eventually, the light would be redshifted so much it becomes undetectable, its energy diluted by the growing fabric of space. From our perspective, it would vanish into the void, not by hitting a wall, but by fading into infinity. Of course, what about the multiverse, which isn't part of the standard universe? Could a signal cross over? If there are other worlds, maybe as nearby bubbles or brains, there are versions of brain cosmology that say universes may be stacked or floating inside a bigger bulk. Although not proven, it's possible that leaks could happen between brains. If this is true, gravity is the weakest force, so it's often thought of as a possible crosser. This could explain why it's so much weaker than the other forces. It could be leaking into other dimensions. Something like gravity might be able to cross dimensions. What about information? Theoretical scientists have thought about wormholes, which are bridges through spacetime that could connect not only different parts of our world, but also whole other universes. One way for a message to get to another part of the universe would be to send it through a wormhole. Wormholes, on the other hand, are still just ideas. If they exist, they are probably not stable, especially for something as delicate as electromagnetic data. There is also the idea of quantum entanglement, the strange action at a distance that Einstein famously didn't believe in. Some people wonder if entanglement could be used to talk to people in other universes. Quantum theory, on the other hand, does not allow transmission faster than light, and entanglement can't be used to send information in the usual way. It's a dead end for now. Still, if there were advanced societies that wanted to send a signal to other universes, they might have hidden it in gravity waves or the cosmic background radiation. Or maybe their messages are so strange that we wouldn't know what they mean, even if they were right in front of us. Are we the edge of another universe? The universe is so big that it's hard to imagine. But what if, in some strange way, we're not the main character? What if we're someone else's cosmic mystery? What if the edge of our visible universe isn't only the edge of our own universe, but also the edge of another? It's a crazy thought. What if we are the edge of another universe? In multiverse theories, especially those that talk about bubble worlds that form during cosmic inflation, the idea that there are many universes at the same time is more than just science fiction. It's possible that these worlds are all squished together in a big cloud of cosmic foam. Each bubble is growing and changing, and they may sometimes bump into or affect each other. But in this setting, the word location is hard to define. Someone from another world in this realm might see ours as an edge they can never reach, just like we see ours as an edge we can never cross. From their point of view, we might just be a faint shimmer in the void, a strange gravity event, a faint design in the background. They might have something like the cosmic microwave background, which is full of strange patterns that make them think we might be alive. The same way we wonder if the cold spot in our CMB shows that there is another universe nearby, they might also wonder about their own cold spot, which we made. This is the observer's role turned upside down. We usually think of ourselves as the explorers, searchers, and edge pushers. But this thought makes it sound like we could also be what is beyond someone else's edge. A line, a fence, a puzzle, a place they will never get to but always wish they could. In some models of the multiverse, each universe is causally disconnected, meaning no matter how close they may be in a higher dimensional sense, no signal or traveler could ever cross over. The edges between them are permanent and impermeable. But in others, particularly those informed by brain cosmology, there might be subtle interactions. Gravity could seep through, particles could tunnel, and in these moments, the boundary becomes a shared space, however abstract. It's even possible in models of eternal inflation that universes are born from collisions, one bubble smashing into another. The marks left by such a collision might be embedded in the geometry of space. If such a thing happened long ago, we might be the product of someone else's universe brushing up against us, and in turn, our own cosmic edge might be the scar from that ancient encounter. As we gaze out at the edge of the observable universe, we are really staring into a question mark, one that challenges not only physics, but also philosophy, imagination, and the very meaning of existence. Whether there is another universe beyond, or we are cradled alone in a vast cosmic bubble, one thing is certain: the search will never end. Because in asking what's beyond, we are really asking who we are and how far we are willing to go to find out. If this journey has sparked your curiosity, consider subscribing for more mind-expanding explorations of science, wonder, and the unknown. And let us know in the comments, what do you believe lies just outside the universe?